In this lecture, we're going to talk about HR diagrams. So let's talk about, what do you think? What colors are stars? Are brighter stars hotter? What sizes are stars? Are most stars isolated from other stars as the sun is? Here we have a picture of Orion. Here you can see Orion's belt. This is Betelgeuse, Bellatrix, and Rigel down here. So also here you can see Sirius, which is called the dog star. This is part of Canis Major, which is the dog constellation. So several stars in and around the constellation Orion are labeled with their names and apparent magnitudes. And remember, apparent magnitude is how bright it appears to us from the Earth. Absolute magnitude, remember, is the actual brightness of the star. So for us, the brighter it is, the lower the number, or the more negative the number. The dimmer it is, the more positive the number. So here you can see the brightest object we have in our sky is negative 26.7. That's our sun. A full moon is negative 12.6. Sirius, which is right here, is a negative 1.44. Our eye's limit is plus 6.0. Anything dimmer than plus 6, we can't see. We can see plus 10 with binoculars. Notice Pluto is plus 15. That means you cannot see Pluto with the naked eye or with binoculars. You would need another telescope for that. Okay, so astronomers give the brightness of objects in the sky by apparent magnitudes. Stars visible to the naked eye have magnitudes above m equals plus 6. So that means plus 5, plus 4, 0, negative 4, negatives 10, anything. And again, remember, we go all the way to 0, and then we go more negative. Okay, also remember from our unit on radiation, we talked about black body curves, and those black body curves can tell us the temperature of stars. So notice here on the left, we have a red-ish star. This is actually infrared, okay, and this is about 3,000 Kelvin. Here's our sun. Our sun has a temperature of about 5,800 Kelvin. Or yeah, 5,800. And for an infrared star, which peaks in, the UV star, bluish star, it's going to peak in the UV and have more violet and blue colors than the reds and the yellows. So blue stars are going to be a much higher temperature, about 10,000 Kelvin for this one. So again, hottest stars are going to be blue in color. Medium stars are going to be orange yellowish in color. Coolest stars are going to be reddish in color. Okay, and again, remember from our previous coursework in temperatures, we also talked about spectral classes. This is where the color and temperature were put together with what we call a spectral class letter. So O would be a fine guy / girl, kiss me. So O, B, A, F, G, K, M. There are letters below M, and there are other letters involved in this. We're not worried so much about those. So we're only worried about these right here. So O stars are going to be your blue violet. They're going to be the hottest temperatures. Your M stars are going to be your coldest temperatures. Our sun is a G2 star. Okay, so that sits at the upper end of the G. The smaller the number after the letter, the higher the temperature. So we're fairly close to being an F star. Okay, this is called the Hertzsprung-Russell diagram, or the HR diagram. Typically, it's plotted with temperature on the horizontal and magnitude or luminosity on the vertical. It can be absolute magnitude, it can be luminosity with respect to the sun's luminosity, or it can be apparent magnitude. It doesn't matter. So this is going to be sort of like your how bright it is, and this is going to be the temperature. So what you'll see here is that we've plotted about 50 stars here. You'll notice that most of the stars seem to follow along this band. This is called the main sequence. Down here, notice you have a grouping of stars. Okay, these are your white dwarfs. Okay. Notice that you have stars that are peeled off of the main sequence and sit here. These are your red giants. Up here you have more stars. These are called your red supergiants. Okay, the ones that are really cool that are over here and very bright, those are your supergiants, and these are your giants. Red giants here, red supergiants here. Okay, main sequence, white dwarfs. So those are the parts of your HR diagram. Okay, again, this is called the main sequence. This is where most of your stars are going to sit when you plot them. So if you take a whole group of the brightest stars in our galaxy, this is where they're going to line up. You're then going to end up with some stars that are off of the main sequence in the red area here. These are your giants. These are your supergiants up here. And then you have your white dwarfs down here. Notice here that you have your spectral class, which is also the color of the star. M stars are red in color. O stars are actually ultraviolet. B stars are going to be blue and whitish. And then right in here, where you get into your A and Fs, that's where you start getting into your white stars. So star brightness is plotted against star spectral types, which is the temperature or the color. Both mean the same thing. The brightness and the spectral type are related. Main sequence stars, where fusing hydrogen to helium is taking place, fall along the red curve, which we call the main sequence. And again, notice they're called main sequence stars. Giants are to the upper right, and supergiants are on top of those. White dwarfs are below the main sequence. So here is a diagram which will help you immensely in answering any questions that I can give you about the HR diagram. If I say, what stars will you find in the lower left-hand corner? They will be hot and dim. Notice the temperature is high. Notice that the luminosity is low. If I say lower right-hand corner, those are going to be cooler stars. Notice the temperature, but they're also going to be dim. Notice the luminosity. Now be careful. This is the 10 to the minus 4, not negative. Okay, so this is also compared to the sun. The sun is right in the middle. Okay, anything lower than that is smaller than the sun. Anything higher than this is larger than the sun. Okay, if I said to you, what's in the upper right-hand corner? Cold, but also bright. What's in the upper left-hand corner? Hot, but also bright. Okay, so you can have cold, bright stars, and you can have hot, bright stars. You can have hot, dim stars, and you can have cool, dim stars. Okay, so it just matters about the size of the star. So the size of the star is important. Hotter stars are brighter than cooler stars of the same size. Keep that in mind. So bigger stars are brighter than smaller stars when you look at the same temperature. So this is where it gets a little bit complicated. If I have a hot, bright star that is large, it's going to be even brighter. If I have a hot, small star it's going to be dimmer. Okay, so hot stars are brighter than cooler stars of the same size. Bright stars are brighter than the smaller stars of the same temperature. So the brightest stars are the biggest, hottest ones. Okay, this is the formula that you can use to determine that. This is the brightness, this is the size, this is the temperature. The larger this is, the higher this is. The smaller this is, the smaller this is. Okay, when you have the same temperature. Okay, so mass, temperature, brightness also matters. If you look at this, this is looking at the luminosity of the sun, okay? These are smaller and these are larger. Notice how it seems to form this straight line, this diagonal straight line. So smaller stars are cooler and dimmer. Larger stars are hotter and brighter. So each dot is a main sequence star. The dot's number is the mass of that star with respect to the sun. So the sun is at 1. This is 1.4 times more massive, 1.6 times more massive, 7.6 times more massive. Okay, more mass, brighter, hotter. Less mass, cooler, dimmer. So mass, brightness, and temperature of main sequence stars increase from the lower right to the upper left. And that ends our lecture on HR diagrams.